So first, I want to thank the organizers for invitation. It's very difficult to get here because it's very, very far. But I'm very glad I made the trip. It's a very nice place and very nice conference. So thank you. So I will talk about GCD, ABC, and hyperbolicity. So since it's the last talk, everything will be very easy, and we just enjoy it. Okay, nothing technical. Okay, so I will introduce what is GCD here, and then I will tell you why GCD implies BC, and then we will get some motivation from function field case, and then we'll back to the complex case. Okay, so as the theme of this workshop, so we are talking about hyperbolicity, and so one natural question here is, so suppose, also I will stay on projective space the whole talk. So suppose you have an analytical map into projective space, and then you want to ask how does it intersect with the hypersurface. Okay, and then we have this second theorem. Then it tells you if you have 2n plus 1 hypersurface in general position, then it must be constant. Okay, so how does this thing tell us? This tells us, so actually you cannot, so in general, an entire curve must intersect hypersurface. So, okay, and so if we miss too many hypersurface, then it has to be constant. So this is, so for divisors, it has to intersect. And then the question is, so what do we expect for some variety of codimension 2? And intuitively, we would think it should not intersect, right? Then the question is, how do you formulate such a thing? Okay. So bear with me for just 2 slides. We need to make some definition, but this is just complex analysis. So very simple one, so bear with me. So suppose we have a meromorphic function, and then it's very natural you want to define the order of 0. Okay, so this is just order of 0. And then we have counting function. We want to sum up all the order of 0 and with weight. And then as we have seen in the previous talk, then we will do this truncation. So if you have order very high, then you truncate to n. So means if you have n squared, you only count n. And then for 2 functions, what do we mean about the GCD? So it means the common 0. So it's very natural to define this as the minimal 0 order. Okay. So these are the things we need. And then after you define counting function, then we need to say how big or how small they are. So we need some quantity to define it. So like we need the absolute value, and here is the thing we define. So suppose you have a map into projective space, and then you can make them entire function without common zeros. Then you can define characteristic function. So the characteristic function just measure how large is the map. And then we want to study how it intersects with divisors, hypersurface. So they are defined by polynomials, unvariable. So let's take a homogeneous polynomial in over C with n plus 1 variable. Okay, and then in the geometry term, we want to study how this map intersect with the hypersurface defined by this polynomial. But we can just define, because we already make this entire function without common 0, so we can just make a definition of the counting function of f composed with small f. Okay, so this makes sense, right? And then how do we define intersection of 2 subvarieties of subvariety of codimension 2. So it would be intersection of two hypersurface. And so therefore, we just take the defining equation, and then we want to see how this map goes through the intersection of two hypersurface. And in this case, of course, then we define it is GCD of the map you plug in. Okay, and this one we expect they should be small. Okay, so that's the end of the definition. I hope it's okay. And then in 2005, Silverman proved the number theory case. So he said if you assume Vojta's main conjecture, it would imply a GCD inequality. So Vojta's main conjecture would be the Griffith conjecture, I think, at least in the earlier talk. Okay. And so let's transfer his result in number field to the complex case. So in complex case, let's take one simple example. So suppose you have an entire curve into Pn. Okay, and again, you assume they are reduced. Then you want to compute their GCD, those things we have defined. And then, according to this machinery, it will prove that it's small. However, there is a term on counting function of the 0. So it's a bit unfortunate here. So you would have this term here. And this is already, so Silverman get this by applying a very, very strong conjecture. Okay, and then you can even apply a stronger conjecture. So if you apply a general ABC conjecture, then you can make this counting function as a truncated one. Okay, so this is what following Silverman's argument you can get this. Okay.
What does the less than or equal to exceptional mean?
Oh, it means it's the inequality hold outside the binary back major.
So for like large enough R.
Yeah. That's fine. Okay, so Silverman's result depend on Vojta's main conjecture, but we were able to prove GCD theorem with Levin, and what we prove is the following. So we have this term here. However, for this term, we have some constant, but this constant is large. Unlike Silverman has actually had one there. So, but we don't assume anything. So this is a theorem. Okay, but even this is large, but as you can see, there are some cases you can treat here. So, for example, if Fi is unit, if Fi is like exponential, has no zero, no pole, then you don't have this term. Okay, so somehow we can control this term by making some assumption on the entire curve. So for example, if Fi are unit, they are gone. Or if their growth is very slow, it's a small function, then it is fine. And then the other case is, so this Fi has if they have very, very high multiplicity, and then this term, this will become very small if they have very high multiplicity, and so compare with the characteristic. So this is also a case that we can control. So at least we can control this type of problems.
Can I just ask a question about the first line? Like just to make, I'm just trying to parse it like sort of in layman's terms. So the left-hand side, you're saying it's the number of times that this curve meets a codimension 2 set.
Yes.
And then the right-hand side, there's some term that's controlled by like the degree or like how complicated.
Yeah. This is like if it's algebraic, it's a rational curve with just degree of the
And then the last term is
so
how many times it meets just f.
So Fi is the entire function, so it has zeros. Mm-hmm. So this tells you how many zeros do you have for Fi.
Okay.
Yeah. Okay? Okay, so now let's see how GCD imply ABC. So actually this is very, very easy, but somehow it works. So suppose we have a homogeneous two polynomial. And so we have, so let's look at the unit case only. So we can write G1, G2 are unit. And then we want to study G evaluator, capital G evaluator, the map. And then let's take a derivative. So, okay, let's not do this. So you take a derivative, you get this one. And then let's rewrite again. So we rewrite G1 prime over G1 and then times G1 squared. So this is go back to Borel. That's what he did. Okay. And so now let's define another polynomial. So let's define a polynomial which depends on the map and the homogeneous polynomial. And so this will be the coefficient. And this is the variable, coefficient variable. Okay, so the way we define it, we know this is a polynomial. And when you evaluate at a G, it's just this capital G prime. So it's the derivative. Okay, so now let's see. So if the order is bigger than, if the order of 0 is bigger than 1 at A, and then apparently, because this will be the derivative, this will be the order of GG minus 1. Okay, so of course this inequality hold. Okay, so very simple estimate. And then let's just take the whole thing together. So for this side, if it's 0, then nothing happened. So we only have to see if order is bigger than 1. And so this part tells you the counting function. And this part is a truncation. So when it has a 0, you count only 1. So we have this side. And for this side, when we take a summation together, it's just the counting function of two polynomials. Is it okay?
Is A a point?
A is a point in the complex plane. Yeah. Okay. And so you have a function. You want to see how the 0 order at Z minus A. So you just take Taylor expansion and then see the 0 term. Okay. So as you can see now, we transfer the problem. So on this side, it doesn't work anymore. So, oh, okay. So on this side, so what do we calculate here? This side is telling you how many multiple 0 do you have? Okay, and so this actually tell you the number of multiple 0 can have a bound by the GCD. Okay. Okay, so now this is what we get. Oh, it's back. So this is what we get. Okay, and then earlier you have seen what is the second-man theorem. The second-man theorem basically tell you if you, so in our case we have the polynomial G, and then we have a coordinate hyperplane. So we have 4 components. So as you can see in the morning talk, you have G, but then because the coordinate point are unit, so when you are computing counting function, so this part remain. The other part are counting 0 of the coordinate, but because we are making coordinate to be unit, so you have no 0. So you have actually 4 terms here, but 3 terms vanish. And then for here, because this is degree D, so what you get is 2 minus epsilon of the characteristic function. Okay, so let's see here. So we have this inequality, and for this counting function, we have an upper bound, we have a lower bound. And so in other words, we get upper bound for the truncation. Okay. And so if suppose we can prove the GCD is small, and then we can find the first truncation greater or equal than this height. Okay, so this is what we call ABC theorem for general ABC theorem. But in this case, we already assumed the 3 units. Okay. Okay, so in other words, we have second main theorem plus GCD would imply ABC. So any questions so far? Okay, so life is not so easy. So let's see what we have done here. So we starting with a homogeneous polynomial with a coefficient over C, over a constant. But then we choose another polynomial. And the polynomial we choose is functions. And it also depends on G. So it's not over C any longer. It's over some C and then with functions. Okay. But remember, what do we choose here? We choose G1, G2 to be unit. And so if it's a unit, then by the first we know for this are unit, so you don't have a counting part because the pole comes from the 0 of G1 and 0 of pole of G1. So if it's a unit, you don't have counting part. And then proximity part is always small by logarithmic lemma. So in this case, we do know the characteristic function of this G prime over G is a small function. So you can just think if you have an exponential of something, then you take a derivative, then you divide the exponential of the function. You only get the exponent. Okay, so this is a small function. So it means, well, we are not in a perfect world. It's not over C, but it's not out of control. So it just means we need to work a little bit harder. So we need a GCD theorem for polynomials, but not just for constant. You need to working with the so-called slow growth moving target problem. Okay, so Levin and I actually already did this part. So suppose the slow growth means so you can define the characteristic function just as to measure how large is the function, and suppose the characteristic function is small, and then this is a field, then we call this as KF. And we actually can prove if you have an entire function without zeros, GIR entire function without zeros, and if you want to evaluate two homogeneous polynomial with a coefficient to be slow function, and then you can have a GCD estimate. Under the assumption, if G1 to Gn are multiplicative independent modulo the small function. Okay. So the GCD part is okay. And then after you have GCD part, then you can have ABC with even coefficient, not just constant. You can with moving. You have some small function as your coefficients. Okay, and the statement is so again this only treat the unit case, and but the coefficient can be a small function, and again you have multiplicative independent modulo. This is the condition, and then you can compute the multiplicative the double zeros. And then again, you need the second main theorem. So you assume it's a general position, and then you can have the ABC estimate. Okay, so so after we did this, actually, so we know that you can do Green-Griffith conjecture for n+1 component. So so for Pn, D would be n+1 component, and it's a hypersurface. So originally the hypersurfaces are defined over C, but now you can define over functions, small functions. Okay, and then, well, what does it help us? Actually, I was very happy about this result because as you can see, this is the polynomial we can study. So we can study a polynomial, FIR function are polynomials, and then we can plug in function which is exponential of polynomial. Okay, and this exponential polynomial has been studied by Ritz in 60s and many people. And so the reason I'm interested in studying the exponential polynomial because it's the analog of linear recurrence in number theory. And so a linear recurrence is written down as this kind of form. And so, so there are many arithmetic properties you can study for linear recurrence, and supposedly that kind of property should have a statement for exponential polynomial. Okay. Okay, but it also has a disadvantage. So, for example, if you remember, we started with a polynomial. We can start with a polynomial over C, but our statement still tell you you need a multiplicative independent over a small field. Okay, so in other words, this method does not recover Noguchi, Winkelmann, and Yamanoui's result in the corresponding case. Because for over C, of course, you want the extensional set to be defined over C. But our result is like you have something over a small field. So this is the thing that doesn't work out very well in our prior project. Okay, so it just means we have to work harder, right? So let me recall Green-Griffith-Lang conjecture. So I'll not follow previous definition. I follow Noguchi, Winkelmann's book. So the conjecture is if you have a smooth projective variety, general type, and then the first result is first conjecture is every entire curve is algebraic degenerate. Okay, and then the second one is the one you see before. So you can find the Zariski closed set proper and containing all the entire curve. Okay, and then we will call B as a strong Green-Griffith-Lang conjecture. Okay, I think this is okay because sometimes A is already very difficult, so let's make life easier. Okay, so okay, so now, okay, so let me just keep in mind. So there are two results. Two conjecture. First, just assume algebraic independent. The second is you find the Zariski closed set. Everything sits in there. Okay, so so after that, we try to work out a function field case, and function field. So what do we mean function field here? So we mean function field is a irreducible non-singular projective curve. And here it's just over C. So like a compact Riemann surface. And so K would denote as a function field of R. So when genus equal to 0, it's just rational functions. And then for function field, we can, at every point, we can also define a valuation. And then you can define so you want to see how this map finishes at the point P. And so this is the order to evaluate the number of 0. And for function fields, because if it's a function field, it's an algebraic function without 0 will be constant. So we always have to pick out some S. And then this is like the entire function. This is like a unit. And then we define the number of 0 outside S. And then this doing truncation, and then you can doing GCD. GCD is counting how many 0 outside S, common 0 outside the finite set S. And then you can also define height. So the height is the characteristic function, and this is for functions. Okay. So it's okay. We will use it a little bit. So if you don't remember it. Okay. So the point is here. So for function field, there are two viewpoints. So function field is something in between number field and Levin theory for complex. On one hand, because you see this valuation, since you have product, you have number of 0 equal to number of pole. So this is the product formula for number field. And then for number field, you cannot take a derivative. It's so bad. But for function field, you can take a derivative. So therefore, it means everything you can do, not everything. I mean, since you can do in the Levin theory, there is a hope to do it for function field. Okay, so function field is really something sitting in there. You can see two sides of thing. Okay, so for function field, you can let's say we write F, but this F0 to Fn are function element in function field. So it's an algebraic function. And you can realize this as a point in P and K. Okay, but you can also realize this as a Morphism from C to projective space.
Is C the same thing you were calling R on the previous slide? Like the K is the function field of C?
Oh, yeah, you're right. You remember, sorry, it's R. Yeah, sorry, this is the curve. So I forgot, I usually use C. In here, I use R, so it's R. Yeah, okay, thank you. And so there are two ways to see things for function field. And also remember, this is the function field of a curve, so the transcendence degree is 1. And now I have F0 to Fn are elements in function field. So the transcendence degree is only 1. So it means those things are algebraically dependent. So this tells us when we try to use Levin theory kind of technique, you do not say those functions are algebraic independent, because they must be algebraic dependent. Okay, so I actually have seen paper for function field, and the assumption is if they are algebraic independent, blah, blah, blah. And so for function field, we usually state like a Green-Griffith-Lang conjecture in function field, which we will call it as the Lang-Vojta Conjecture, as the number field case. But in this case, this Green-Griffith-Lang conjecture you cannot formulate as with the algebraic independent condition. So you must go to strong. So you must go to the strong GGL. So you have to find the exceptional set. Okay, and similar for Vojta's general ABC conjecture for function field, you must find the exceptional set. So one way for function field is harder in the case if you compare with the easier Green-Griffith-Lang conjecture. Okay, so this is a few points. So, so in other words, so in our very recent paper, we were able to see how to overcome this difficulty. So the statement, this is the statement of our theorem. So you start with a polynomial over a function field. And because it's S unit, I'll do the affine case. And so suppose this G has no monomial factor and no repeated factors. And then you fix the issue. And then you really can find a proper subset. Okay, and then you find a number. Those things are computable. And then for all the units, on top of units, outside of this proper subset, we have either the height is bounded, or you have bound on multiplicative zero, double zeros, and or you have the ABC. Okay, and let me just say, this thing doesn't happen in number field because if you have a height bound, and for number field it's already implied finiteness. But for function field, if you have a height bound, it can be like a t and a constant multiple of t. They all have height 1. So we have some extra condition here. Okay, and moreover, so for function field, the things should be effective. And so this C0, the degree of Z, can be effective bounded. And this exceptional set can be formulated explicitly, means there is a way to compute them. And finally, we finally solve the thing about if you started from over a constant, and the exceptional set has to define over a constant. So this would go back to complete the part of this classical case. Okay. Okay, so let me explain this in the complex case. So let's see what's the basic idea here. So let's start with unit. Okay, and then we have we make the short notation here. Okay. Now let's write gx in this form, and then let's do it again. So we can define a polynomial which depends on the unit, on the equation, on the function you first give. And then this is the way we try to make the following inequality hold. Okay, so in other words, now we define a polynomial of the same degree as G, and then when you plug in G, it is equal to the derivative. And as we have seen, this would be if you want to bound the double zero, it would be bounded by the GCD of two polynomials. Okay, so let me explain a little bit how the GCD theorem goes. So as usually, now everything depends on the second theorem. So, and usually the technique is you start with something in Pn, then you want to embed it. So you start in Pn, and things can be maybe nonlinear, and then we try to embed it to higher degree, higher space, higher dimensional space. And then the thing you are interested in become linear. And then you can apply the second theorem, because second theorem was for linear. But it's not so easy. You need to very carefully count the thing you are interested in. That's the hard part. Okay. So the thing is, you start with an issue. Then you need to do embedding. So you embed with monomial of degree m. Then you need to carefully choose which monomial has to involve in here. Okay, then you embed to another projection space. And then you can show, suppose after the embedding, and if it's linearly non-degenerate, then you can prove, use second-man theorem to prove the GCD is small. Okay, and so what if they are linearly degenerate? But if it's linearly degenerate, it simply means you have some monomial of G, and then they sum together with some coefficient in slow field. And so this is the Borel lemma we can use. So you can modify Borel lemma and just to show that just to show so as Borel lemma. So this M is the space the degree of a monomial, and then we can show they are actually multiplicative dependent on Kg. So means they sum together to Kg. Okay. So this is how this second GCD theorem is organized. So after we did this, so here is the thing. So as you can see, remember we used GCD theorem, but the GCD theorem is applied with a polynomial and another polynomial, and this polynomial actually depends on the function. So in other words, you apply GCD theorem every time when you have a function you want to consider. So it's kind of you are repeatedly use the GCD theorem. But over here, what is controlled? So remember, we give an epsilon, and then we find the embedding, and this part is universal for every map. So in other words, this M is controlled. So in other words, we know this multiplicative dependence is up to order M. Okay, and this is controlled for every function. And so the key point here is after you have this, then we have to do induction. Okay, and the induction will rely on spatialization. But let me try to do surface case first, so you see how this is going. So by the previous, you apply the first GCD theorem, and then you find something is slow growth, and then you can assume this M1, M2 is coprime. Okay, and in this case, you can find the A and B integers such that M1A plus M2B equal to 1. So you can find another beta, and you can write U1, U2 back to lambda and beta. So in other words, what we are doing here is first you have a transformation of a monomial, and then you can try to make them to be a bijection. Okay, so in other words, you make a bijection on the monomial. And then we'll start to do reduction. So at the first, we have G. G is so sorry, this is just a G. Okay, so if we have polynomial affine case, so we have X and Y, and here you make X you change X and Y into this new form. And then you have T and lambda. And another polynomial, just you take out all the monomial factors, so such that the B of 0, 0 is a constant. There is a constant term there. Okay. So, and later, here is the thing. So this is the thing already small. So we want to, we want to make an induction on this lambda. So now we make a transformation. So at first we have G is a square free. And because this is a bijection, so the new polynomial is also square free. And then later we want to plug in lambda. And we want to see whether the new polynomial, one variable, is still square free. Okay, so because this is square free, so we take a resultant over t. And this would not be identical to 0. Okay, so the resultant will be a polynomial in this C lambda. And so if we find all the 0 of the resultant, then outside of those points, it will be square free. So first, we make a specialization here. So we take lambda, which is not the 0 of the resultant. And so in this case, we also can see if your polynomial is starting from C, then the resultant is still in C. Okay. So in this case, we take out those resultant, and those resultant give you exceptional set, and so they are in this type of form. Okay. So then we can start it to do induction. So the induction step is you take lambda not to be in the result of resultant, and then now t is the remaining variable, and so because we want to counter all these things. And let's go back a little bit. So here is the equation. And the thing is now everything is unit. So you don't need to worry about this part. And so when you are computing this counting function, then you have nothing to worry. They are really equal. Okay. And so suppose you are not in the exceptional set, then this is just really a polynomial with no double zero, and then we know how to do the one variable thing. So you can show this is small. Okay, and then you get the contradiction. Okay, so this is how things are done for the n equal to 2. So as you can see, everything, so what we have to do is try to make, during the induction process, you want, after you specialize, and you want the remaining polynomial to be square free. Okay, so here we prove specialization lemma. So this is used for induction. So basically, so this is the thing we want to specialize. And this originally you have a polynomial in here. And the theorem tells you originally in this polynomial, it doesn't, in more variable, you don't have repeated irreducible factor. And then the exceptional set you can find is actually a Zariski cross set in the first part. Okay, so you want to specialize in the first part. And then you can find some exceptional set. So if this lambda is outside of this exceptional set, then after specialization, you have a polynomial, which has no monomial and repeated factors. And so this is the way we can do induction. Okay. And the proof involves only Wronski. Only resultant. So you can explicitly find out where the exceptional set sit. Okay, so that's about how we did this problem. Okay, so let me just say a few words. So first, the technique actually first came from Lang-Vojta when they tried to study Lang-Vojta conjecture for one cone and two lines. Okay, and also for ramified cover of GM square. Okay, but Lang-Vojta told me the idea studied from Borel. so okay. And then you have non-split case by Tzu-Yueh and Tzu-Yueh. And we actually generalize the result to n greater or equal than 2. Okay, so for complex case, so this method actually lead to the corresponding result of Noguchi, Finkelman, Yamanoi, and then they assume algebraic non-degenerate. And here we can actually find the exceptional set. And we have an explicit way to find the exceptional set. Okay. So let me just state, so for the complex case, what we prove is if you have a homogeneous polynomial, and if coordinate hyperplane, G is in general position with coordinate hyperplane. And if you have a tuple of units, and then you find a Zariski cross set, such if the image is not contained in the proper Zariski cross subset, then you have a truncated second-man theorem. Okay. So further results. So as you can see here, as I indicated, so everything is depend on, you don't just this method doesn't just work for unit. It also works for as long as the 0 and pole are small. So in this case, it's working. Okay. And furthermore, this method also works for Campana's orbifold conjecture. So in other words, if you have orbifold curve, and then if you have a high multiplicity on coordinates, and as I explained, the counting function, because we have first truncation, so the counting function would be very small. However, it's small, but it's the same growth of the characteristic function. So in other words, for this Campana's orbifold conjecture, you need to do second-man theorem with the same growth. And you need to prove GCD theorem with the same growth. And then, but again, for this induction process, it doesn't work anymore for this Campana case because you can have 0. And then doing this monomial transformation would mess up the 0 and pole. But for n equal to 2, you can compute more carefully, and it does work. Okay, and then you can settle down the exceptional set. So for example, this case, and then so this is to show the defect. So I will not say too much about this. This is simply tell us the defect, if defect equal to n plus 1, would imply those characteristic function of those, the counting function of the DI are small functions. And so this method would tell us it's not possible. Okay, and for this case, we can also find the explicit exceptional set. And again, for the case of log general type rainbow cover over GMN, and this method also lead to find the exceptional set. And historically also, okay, so our result B is actually inspired by the result of Chen, Huang, San, and C. So our speaker, our organizer, both not here. Okay, so they're very recent result, and they need to do something quite fancy, and they assume algebraic degeneracy, non-degeneracy. And our method is kind of elementary. Okay, and furthermore, we can find the exceptional set for the defect relation. And then for the exceptional set, for surface case, so actually, Noguchi-Winkelmann Yamanoi already has the result. And then for higher dimensional, for semi-abelian variety, I think it's Kazaro then Yamanoi's result. Okay, so this is about all of the story that we have worked on. Yeah, so thank you.
Is there any comments or questions?
You said you could explicitly compute these exceptional loci in some examples. Do you have like an estimate for what the degree is, or?
Yeah, we have what?
An estimate for what the degree is, or like what the description is?
That's a very good question. We are working on it. Actually, the estimate is not very good. So because as you can see, it still rely on this GCD theorem. And we actually have to do very high, very, very large. So, so far, not very good. It can be estimated, but it will be very large. And if you want to see Aaron Levin, his students has worked out some estimate. Yeah.
You mentioned this, well, not an application, but the case of orbifold. And then, do you have somehow a bound on the multiplicity of the orbifold? Is this, or is it
bound of what?
On the multiplicities of the orbifold curve you are considering?
No. Yeah. So our theorem tell you can find something, but it's the largest number. So yeah, it's a bit unfortunate, but so there are more things to work out.
Anything else? So in that case, thanks.
So on behalf of our speakers and participants, I think we want to thank the organizers for very hard work and putting everything together and make us very enjoyable conference. So thank you.